Thank you, Carolyn, for the introduction. I think I'm the first computer science talk in the last 3 or 4 years of CSGF conferences I've been to. So I think I have the unique opportunity of giving a talk that nobody understands. But also I think I have the opportunity to actually give a talk that is useful to everybody, because I think the overwhelming majority of you will have to deal with computer science to a relatively heavy extent, though a lot of people don't like to do it and don't like to talk about. And so what I will like to focus this talk on is not so much the depth of my thesis research, but the way we think about algorithms from a theoretical perspective and how we develop new parallel scalable algorithms. And I hope that that will be useful to a large majority of you. I guess I want to have kind of a talk thesis that is maybe somewhat controversial, especially in this audience. And that is that I think numerical methods and algorithms should be developed with a priori consideration for communication cost and for parallelism. That's basically saying that you can't just think about the amount of work your algorithm does and even just how well that work parallelizes, but also how much communication this algorithm will do. And you have to think about that before you even implement the algorithm, or at least that's the best way, I think, to design algorithms that are actually better than what we've had in the past. So the talk will basically start, and I will go into quite a bit of depth into basically how we measure communication costs and explain a bit about the properties of communication on what I will say is a modern computer, because I don't want to use the loaded words supercomputer, cluster, or shared memory machine, because I think I want to focus on the theoretical perspective, and what I will say should apply to all of these architectures. Then I will talk a little bit about this weird thing we do called communication lower bounds, which to some people seem completely irrelevant because they don't seem to immediately help you come up with an algorithm, but I will explain how they do. And then I'll actually go into some examples from my research in dense linear algebra and from applications in sparse linear algebra, which should be very relevant to a lot of the applications you guys work on. So what is a modern computer? It's a parallel computer. There are no more sequential computers, just as there's no more DOS machines. So I think parallelism is there and prevalent. So if you design an algorithm that is sequential and then to try to parallelize it later, that's kind of not thinking about the right computer model. Further, this computer has, I think, 3 most fundamental costs. That's the cost per computation, the cost per communication of a byte, so of a single word of a single piece of data between 2 processes, and the cost of synchronizing processes. And basically what we have now is that the cost of a single computation is much, much less than the cost of a byte transfer, and the cost of a byte transfer is much, much less than the cost of a synchronization between processes. And this is the gap is only going to grow. It's probably, let's say, an order of 1,000 now, might be 10,000 soon. And so one cost I will not talk about so much, but that is important and often should be considered independently of the interprocessor communication cost, which is called the horizontal communication, is the vertical communication cost throughout your memory hierarchy. And that can be sometimes an important factor that these 3 don't fail to account for. But I won't talk about that so much in this talk. So one way of measuring these costs in an algorithm is to consider the volume, the total amount of work that's done, the total amount of communication that's done, and a total number of synchronizations. This seems to measure all the costs, but however, it gives you somewhat weak bounds on your actual execution time. So you have a nice lower bound in execution time, which is all these costs divided by p, the number of processes, but your upper bound in execution time doesn't have a factor of p in it. And the problem is load balance. So just because the total amount of work may be small, that doesn't mean you can actually compute it all in parallel. So a better measure is to consider what's called the critical path cost, and a term that's often abused in parallel computing literature without being properly defined. And that's basically the longest sequence of computations that are dependent or computed sequentially, and the longest sequence of data transfers that are dependent on each other or computed sequentially, and the same thing for synchronizations. And if you measure these costs, you can actually consider them independently, and they will give you tight bounds on the execution time, both at least how much the execution time will be, and as well as at most how much what the execution time will be. And they're also, in some sense, independent of the number of processes, although your schedule for which you measure these might be. So to give a concrete example, let's say we have 3 processes which do some work. These are the blue circles, and communicate back and forth data. And this is just kind of random. So we might consider the critical path for the synchronization cost, which will be the largest amount of diamonds. And the point is that it doesn't stay in one processor. So if you just consider what a single processor does, that might not give you a good bound on the overall execution time if the computation has dependent sequences and is not load balanced. So this might be the critical path of synchronization, but the critical path for bandwidth may be different depending on how much data is actually communicated. And the flop cost may also be a different critical path depending on the weight of the blue circles. OK, so now I want to talk a little bit about how we actually design algorithms and how lower bounds on communication costs play in. So what we do, and I think how one should design theoretical numerical methods with a theoretical computer science basis, is to propose an algorithm. So that's defining how you actually compute and solve your problem. Then do 2 things. Compute a candidate schedule, so a candidate parallelization of the algorithm, and consider what the cost of that schedule is. And typically, people take just this path. And this allows you to obtain an upper bound on the cost, and you might be happy with that if you have a budget. I think usually you don't have a budget. You want to find the best possible algorithm. So to do that, I think and also if you don't attain your budget, you don't necessarily know what to do. You don't know if your schedule isn't good enough or if your algorithm isn't good enough. So what we often do is we do dependency graph analysis, which I will explain a bit after this how we do. Then we obtain from this dependency graph analysis a lower bound on communication costs for the algorithm for any schedule. And if these bounds match for some schedule, we know we've found a good schedule. And now we can check if the budget we had is attained, if the resulting schedule is good, then we're happy. If the budget is exceeded, so the algorithm and schedule are expensive, then we need to go back and find a new algorithm, not a new schedule, because we've shown that there can be no better schedule. And if our lower bound does not match, then we know that we either need to find a tighter bound or we need a better schedule. And this kind of iterative process allows us to show that the algorithm and the schedule are optimal, or figure out when we need to look for a new algorithm and when we need to look for a new schedule, a new parallelization. OK, so how do we actually think about this dependency graph analysis, the dependency graph representation? So we can represent any computation as a dependency graph, where we start with an input of data, form some intermediates. From those intermediates, we form some more intermediates until we get to our output. And what we can then represent is say that this is a graph. So we have some nodes in the graph which correspond to each intermediate value, and edges connecting those intermediate values. And now we want to think about how the properties of that graph, which is independent of a parallelization, it's only dependent on the computation, can tell us something about the communication costs. Well, one thing we can do is just get a simple bound on the computation cost by looking at the longest path through this graph. And that's a path that has to be computed sequentially, that can't be parallelized. So kind of the depth of that graph tells us the amount of parallelism that is present in the computation. What we can do to measure the communication cost, and in particular to lower bound the communication cost, is consider the expansion properties of that graph. Expansion means that we want to look at some subset of the graph, say some volume, and calculate its surface area. So all the nodes, all the edges that lead out of this subset. And that surface area is what really tells us something about the communication costs, the communication bandwidth cost in particular. And formally, we know that at least some process will have to do a piece of the work, so we can lower bound the bandwidth cost by the expansion of the minimum set of that size in the graph. OK, so now to actually get a little bit into my work, I want to talk about synchronization lower bounds and a technique we have for thinking about these. So what we'd like to think about is cases where we have one point out of which many paths expand out and then converge back into another point in the graph. And that kind of expansion, which we actually call bubble expansion, and kind of captures all the interdependent computations that we have to do at a given time in order to progress along some critical path in the computation. And this allows us to bound synchronization. So to be particular, we can consider this diamond DAG, which is very popular, and consider basically the critical path that goes down the middle. And once we have a parallelization, which gives us a coloring, so a black-white two-processor parallelization here, we can think about these kind of bubbles within that parallelization. And we know that all of these black vertices have to be computed sequentially between the next set and the next set and so forth. We care about how fast these grow depending on the number of vertices we go down. So that grows as b squared if we go down b. And we care about the minimum cut of those bubbles. And that tells us the communication costs necessary to compute each piece. And this kind of allows us to formally derive a synchronization trade-off. And I say trade-off because the lower bounds here will manifest themselves as, for synchronization, as trade-offs between synchronization and cost, and synchronization and computational cost, and synchronization and bandwidth cost. So for instance, if you want to parallelize a computation on one processor or two processes, you have to do very little synchronization usually. But if you want, it will usually scale as a number of processes in terms of how much synchronization you need to do, which is not too surprising. What's kind of more surprising from this technique is that we can actually obtain lower bounds on that manifest themselves as trade-off between the communication bandwidth cost and the synchronization costs, both communication costs that are kind of bad and we want to avoid. And we have this equation that if these paths expand in some d dimensions as a d-dimensional object, then we have these types of trade-offs, which are basically proportional to the overall problem size and are independent of the number of processes. So these are actual bounds on execution time. OK, so to give now some examples in dense linear algebra, we can think about Cholesky factorization and obtain some bounds which are basically and show that algorithms we know are optimal for these, including some new algorithms, by thinking about the expansion properties of Cholesky, where these bubbles basically grow as something of the third dimension and have cuts that are planes, so second dimension. And we can lower bound the synchronization because these graphs are path expanders. This is, sorry, an order 3 path expander. What's interesting is that we have basically the same cost, the same similar algorithms for also QR and the singular value decomposition and the symmetric eigenproblem. And so all of these we can kind of lower by a factor of square root c for the bandwidth costs, but we have to pay more in synchronization. And this is better than what people typically do, what, for instance, Linpack does in the top 500 list, where they synchronize order n times and then run it on a million by million matrix and take 8 hours. So I think Linpack is not even representative of dense linear algebra computations anymore, where we really want to run matrices that are 1,000 by 1,000 or 10,000 by 10,000 and do those faster. So I now want to say a couple of words about what it actually takes to achieve all of these for QR, the SVD and LU, which a lot of my work has gone into, but I want to just touch upon. And the point is, for a lot of these, we need to change the actual algorithm. For LU, we need to do a different type of pivoting. We can show that partial pivoting, we can derive lower bounds for it that will have to do that much synchronization cost. For QR, if we want to use householder transformations, which are cheaper, we need to basically do a Bloch-Givens type algorithm on each panel of the matrix, and then reconstruct the householder form. And we need to do kind of linear algebra and prove new numerical bounds on that new algorithm. And for the symmetric singular value decomposition and symmetric eigensolve, instead of kind of directly computing the eigenvalues in one step of the algorithm, reduced to tridiagonal form, the symmetric matrix, we need to reduce it to successively smaller band forms. So again, we need a new algorithm to find something that's more parallel. For all of the kind of previous algorithms for these problems, if we just tried to parallelize them without changing what we did originally, we would provably not be able to do better than before. Okay, so now quickly I want to talk about a little bit about Krylov subspace methods and sparse methods. So this is the formal definition that we proved it for, but let me give an informal definition. We want to take S steps on some mesh, so we have a d-dimensional mesh, and we want to take S steps in time. So the overall computation is d plus 1 dimensional. And at each step, we want to have things interact that are within distance m. So we have these two parameters, d and m. And this is really kind of typical of a lot of computations. If you have a mesh, if you have a particle method, this is what you usually do. And so now to give a very important example of a 1D mesh case and to demonstrate an algorithm that is kind of famous. So what you usually do is you synchronize for every matrix vector multiply, so for every time step. But what you can do instead is synchronize every few time steps and compute as much work as possible on your local piece and advance as much into time as far as possible, and therefore do a lower amount of synchronization. However, as it turns out, to do this and on a more than one-dimensional mesh, you need to do more communication and more work. And we can prove this by application of the same expansion properties that I showed before that may have only seemed relevant for dense linear algebra. And so this is kind of a demonstration for the 2D case. If we want to compute some block, this is the typical surface area that we want to get each step. And this is the overall surface area for 8 steps. If we want to compute this into kind of 8 steps deep and only synchronize once, we need to get a larger volume. So we need to do more communication. OK, that's pretty much it. This is just a summary. And I'd like to quickly thank my collaborators, Nick Knight, Aaron Carson, and Jim Demmel, who directly contributed to this work, as well as Gray Ballard. And I also thank Devin, Jeff, and Eric, whom I all met through CSGF. Jeff and Eric were my practicum coordinators, and I still work with them 2 years and 3 years later. We still collaborate. And many thanks to the Department of Energy Computational Science Graduate Fellowship, which has given me a lot of freedom and allowed me to do some work that's been really independent and fun. Thank you.